understand everything that our lecturer is about to teach us right now in Jesus' name.
Amen.
And at the end of the lecture, we also ask you to give our grace to pass the information swiftly and easily in Jesus' name. And at the end of the day, we shall have up us to glorify your holy name.
Amen.
Just know and pray.
Okay, so we are going to start the class for today. But before we continue with the lecture, I just want to tell you, I just want to present a news about what is happening in the field of artificial intelligence. So it turns out that a few weeks back, the Nobel Prize in Physics and in Chemistry was given to AI. So it was like a very shocking development because we know what physics is. So we've all done physics and we know what physics is all about. So, but it turns out that the Nobel Prize was given for physics and chemistry was given to AI researchers. So these were the two persons that won the AI prize. The Nobel Prize in Physics. So John Hopfield and Gottfried Intel. So they are AI researchers, right? But they won the Nobel Prize in Physics. So it is something that generated a lot of noise in the field of AI, in the field of AI and in physics, because a lot of people thought that they were not supposed to win because given their background, which is in AI. So when they were even interviewed, one of them was interviewed, he was surprised. So Hopfield and Intel, they did not even believe they are going to win. You can see he said he was flabbergasted because this is not like, has never been done before. And even when you look at the comments, the only reason why they were awarded Nobel Prize in Physics was because they developed a paper. So they wrote a paper in 1982 on neural network, and their work was the foundation for the ANN we know today. So the only reason why physics came into play is that in the article, in the paper, they talked about a physics concept. So the concept of like a sand glass, when it's broken and when it's scattered, so it begins to behave in a way that is kind of similar to the neurons. So that was like the only thing they put in the paper that was like physics. So it was really very shocking to the AI community and to the field of the scientific community. And if you go deeper, so this was the reason. So in the paper, they reference the concept of a spin glass. So when it's like scattered, it leads to complex interaction. And that was the only thing that was physics in that paper. And also for chemistry too. So the Nobel Prize for Chemistry too was awarded to AI researchers. So they built an AI model to predict the structure of proteins. So these are researchers in AI, and many people felt that they were not worthy to be awarded Nobel Prize in Physics and in Chemistry. So I just wanted to just tell you what is happening in the field of AI. So let's go back to the lecture of today. So we are going to talk about training the first model. So the model we are going to be training is a linear regression model. And these are the learning objectives. So you should be able to build a simple model. Then you create appropriate loss function and optimizer. So we're talking about what is loss function, what is optimizer. Then you'll be able to understand the main steps of a training loop. So the steps involved when you have like a training loop for an AI task. Then due to checkpoint models to either resume training or development. So we talk about how to save the models, and maybe you want to deploy it for an application. Then you understand the importance of activation functions in deep learning models. So with all of these things, we've kind of mentioned it. So this class is just going to be like introducing you to the Python code involved, so the coding involved, and trying to reinforce the concept, because remember the previous classes I said we are still going to go over some of these concepts that I've said. We are still going to go over it. So we are going to do a recap. So the data sets we are considering, so we are going to go through all of these steps hopefully for this particular class. So the data set we are considering is the UCI data set for AutoMPG data. So let me show you the data set here. So this is the data set we are considering. So it's the AutoMPG data set developed by UCI. So each of the columns in this data set, they represent some features that we are, or some input or some attributes that we're going to be talking about. So the first column is the MPG. So the MPG is the miles per gallon. So that's like an attribute. The second column is the number of cylinders. Then the third column is the dispense column. Then HP is the horsepower rating of the car. Then weight is the weight of the car. Then ACC, you have ACC. Then you have the year. So year is the year when the car was manufactured. Then origin. So this is the origin. Origin is the place in which the car was manufactured. So they used like a kind of encoding. So maybe one represents a particular place where it was manufactured, two represent another location, then three represent another location. Then the last column is the car itself, so the name of the car. So these are the attributes of the car. So this first column is the miles per gallon. So this miles per gallon is actually the target, or we call it the output. So given all of these attributes, we want to be able to make prediction of the miles per gallon. So what is the fuel consumption of the car? So that's what this data set is all about. So the data set has the following features, and it has this output. So this is the output. So we normally put the output on this side, on the right hand side, but at the moment this particular output or the target is on the left hand side. So so I've given you the columns of the data set. So what this piece of code is just doing is to get the data set from this URL, then label it with the column names. But because as we can see, when we look at the data set, the column names are not labeled. So it's to label it with the column. So it's to label it with the column names. Then because there are some missing values in the data set. So this line of code is to remove the missing values. So let's look at the data set again. We can see that if you scan through the data set, sometimes you will see question marks. So like this one here, it's a question mark. So that means that there's no value there. So, and if we just feed all of this into the when we are trying to develop the AI model, it will give us some issues. So we want to remove, you can see this one, there's also a question mark, which is like a missing value. So we want to drop all the missing values in the data set. So that's what came about this line. So we'll drop all the missing values. Then this line is to shuffle it. So shuffling is very important, because if we look at the data set again, we can see that it has a kind of order. Like I said, that this particular column G, is the year of manufacture, the year the car was manufactured. So like these cars were manufactured in 1970, 1971, 1972, 1973, 1974, up to 1982. So it's followed a kind of structure. So we need to like shuffle it, so that, because, can somebody tell me why we need to shuffle it? So I didn't complete my explanation. So just complete the explanation for me. So why do we need to shuffle it? Yes? Exactly. So she's very correct. So the reason why we need to shuffle it is because, you know, I told you that we will split the data set into training, validation, and test set. So if we just put all of this then we split it. It turns out that maybe it's from 1970 to 1978 that will be in the training set. Then maybe from 1979 to 1982, that was what's going to be in the test set. But we don't want that. We want each of the features in each of the different randomness in each of the features to be in both the training, validation, and test sets. So that's why we need to do some shuffling, just like shuffle it around and mix it up to introduce that variety in the training, test, and validation set. So here, these last two lines are to divide the data set. So it's after shuffling. So it's after you shuffle it. This is to shuffle it. So it's after you've shuffled it that you can now divide it into training, validation, and test set. So what this line of code does is that it splits the data. So the data as it is, it contains, let's just give an example. So you can actually split it up. Somebody should come and change the code. So this data set, let's assume that it contains 400 rows. Let's assume it contains 400 rows. So I've showed you the spreadsheet. So let's assume it contains the 400 rows. Then what this line of code, what it's going to do is that the data set has 400 rows. Then it's going to split it into training and validation and test sets, so that the test set is 16%. So 400 times 16 percent is what? 64. So it means that what is in the training and validation is going to be, this we'll calculate it later, then what is in the test set is going to be 64. So if 64 is in the test set, the training and validation, how many rows will? 3. So 336 rows. So that's what this line of code is doing. So for the training and validation, we have 336 rows. Then for the test set, we have 64 rows. Then what this line of code is doing is splitting the training and validation, is trying to split it again, because we first of all we did these two splits. So now we want to split the train and validation. So and it's 0.2. So 336 times 20%. So what would that give you? 67.2. Okay, so that means that for the test set, it's going to be 67. We'll just drop the points because you can look at the data set. We are dealing with rows, so there's nothing like points something. So we just drop the point. Yes? Okay. Sorry. So this will be train and validation. So thank you. So this is the validation. So the validation set is going to be 67 rows. Then the train, so what will be the train set? 336 minus 67. How many? 269. So we have 269 rows. So what these two lines of code is to divide the train set will be 269 rows. The validation set will be 67 rows. Then the test set will be 64 rows. Then when you add everything together, is it going to give you 400? If it doesn't give us 400, that means that we made a mistake somewhere. Did it give us 400? Okay, so it should give you 400, which is the total size of the data. So that's what these lines of code is. So remember, it is important to first of all shuffle it. So before you divide it into train, test, and validation. So after that, we are going to remove the missing values. So what all of this line of code is just doing is that just remove the missing values. So all those question mark, remove the missing values for the train, the validation, and for the test set. So this part has to do with data cleaning. So for this part, we identified the missing values, the NA. So NA simply means not a number, because in AI models, we are majorly dealing with numeric values. Because if you look at this data set here, so all of these are numeric values. The last column was not included in it because it's not a numeric value. So when we looked at all of the columns, there are 1, 2, 3, 4, 5, 6, 7. Then when we look at when we're trying to get the column names, so 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the origin. So here is the origin. So this 8 is the origin of the car. So actually this one the last column was not actually included because it is not a numeric number. So that line of code is to drop the missing values, drop NA. So NA means not a number. So those are the data cleaning we are doing. Then we have to do some data pre-processing. So this data processing is really very important. So we have in that data set, it turns out that the attributes we have, they are divided into continuous attributes and discrete attributes. So these are the continuous attributes and these are the discrete attributes. Yes? Okay, so these are the continuous attributes and these are the discrete attributes. So what are the continuous attributes? So is this blocking? So these are the continuous attributes and these are the discrete attributes. So the continuous attributes are basically the attributes that they are continuous in nature. So they are not divided into categories. So it's what is there in those columns, they are continuous. So they are numeric values and these values is not forming a kind of structure. So that's what we call the continuous attributes. Then the discrete attributes are those that are into categories. We also call them categorical attributes. So this is the number of cylinders, the year of manufacture, and the origin where the car was made. So if we look at the data set, cylinders, so the number of cylinders. So when we look at it, let me try to bring the column for the number of cylinders. So this is the column. This column here, column B, is the number of cylinders. So if you look at it very well, let's just scan through the data set of this column B. So look at it very well. So just by looking at it, how many categories is this cylinder? So we have 8, 4, 6, 3. So if we look at this column, so we call this a discrete attribute because it just has, I think it has 3, 4, 5, 6, 7, and 8. So these are just the categories of the number of cylinder the car has. So we said that it has 1, 2, 3, 4, 5, 6. It has 6 categories or 6 discrete values. So that's why we call it a discrete attribute. So this attribute is the year of manufacture. So it started from 1970 and I think ended in 1982. So from 1970 to 1982. So how many categories? 12 on 13. So it has 13 categories. Then the last one, the origin. The origin. So if you were to scan through the data set, it just has 3. So 1, 2, and 3. So it has 3 categories. So these are the discrete attribute, and we also call it the categorical attribute in the data set. So the others, they are called continuous attributes because they don't form a particular category. If we were to divide like maybe this MPG into categories, it would like take plenty number of categories. So is any particular attribute that just has a specified number of classes. So that's what we call a discrete attribute. So we got the, yes? So the discrete attributes are those ones that have like a fixed number of categories. So like I said, this one has 13 categories, 6 categories, and 3 categories. So for the others, they have larger amount of categories. So like I said, so your question is how to know the number of categories. That is like okay, so there's not really a fixed way of knowing the number of categories. So the only way you can know it is when you look at the data set. So you look at the structure of the data set. Then another way you can know is actually to plot the histogram. So I actually said this for those of you that have watched the video recording for this particular lecture. So these are the continuous attributes. So to answer your question, how do you know if an attribute is discrete or if it is continuous? The way you know is to plot the histogram of all the attributes. So if we plotted the histogram of the continuous attributes, and when we plotted the histogram, you can see when the board was on. When we plotted the histogram, we add like something of this nature. I'm just trying to say. So here represents the that particular attribute. Maybe it started from 0 and it ended at 1000. So that was what was on the x-axis. So what is on the y-axis is the number, the frequency. For instance, if this place is 50, this place is 100, this place is 500. So what the histogram, what it shows on this y-axis is the frequency. So for instance now 50, the value 50, how many times did it occur in the data set? So that's what is here. The number 500, how many times did 500 occur in the data set? You plot it. So when I showed that plot, it looked like this, but it looked like this because it is a continuous attribute. So if it was a discrete attribute, when you do a plot of the histogram, you will see that what is on the x-axis, it will fall into different categories. Because like for instance, this is 13. So this one will fall from 0 to 13. Then in the frequency axis, you will see the number of values for 0, the number of values for 1, the number of values for maybe 5, the number of values for 6. So if you were to do the histogram of the discrete attributes compared to the continuous attributes, for the continuous attributes, you'll be getting a kind of continuous line. But for the discrete attributes, you will get discrete classes. So that's how you know if an attribute, that's how you are able to know if an attribute is discrete or is continuous. So is a plot of the histogram values. So like I said, the plot of the histogram values are the numeric value, the features, then the number of times this value occur. So from the histogram, you should be able to determine whether it's a continuous or it's a discrete attribute. So I will just show the histogram again. Okay, so this is the histogram, right? So when you look at the histogram, you can see that it's continuous in nature. But so this is a plot of the histogram of all the continuous attributes. But if it was discrete, you will actually see something like this. So you are going to see the separate classes. But here, it is very difficult to see the separate classes because their values in the continuum, their values from 100 to 200. But if it was for discrete, you will see the one for 100, the one for 101, the one for 102, and like that. So that's how you know. So we continue. So we separated it into continuous and discrete attributes. So you might be asking that why do we need to separate out the attributes into continuous and discrete? Why can't we just feed everything into the AI model? We are at this point, and the reason why we are doing that is to pre-process. That is the reason why. It's because of what to pre-process the data, want to pre-process the attributes. The way we pre-process continuous attributes are different from the way we process discrete attributes. So that's why we need to first of all separate it out. So now we now talk about how do we pre-process the continuous attributes. So pre-processing the continuous attributes, it involves something we call standardization. And this is the code for the standardization. So what are we trying to do here? So what is standardization? So it turns out that, like I said, we are in the pre-processing step. We are in the pre-processing step, and we have to pre-process the data because we don't want to feed in the data directly into the AI model. And why do we need to pre-process? It turns out that for the continuous attributes, the AI model does better if the range of values in the continuous attributes, if they are within a particular range. So let me put it like that. So let's look at the histogram again. So let's look at this histogram very well. So like I said, this histogram is what is on the x-axis here is the continuous attributes. Then what is on the y-axis is the frequency, how many times they occur in the data set. Like for instance, maybe the value of 100, maybe it occurred maybe 70 times. So maybe the value of 200 in that data set, when you count the number of times it occurred, is like 10 or so. So the same thing with every one of it. So when we look at the range of values, this one is like from 50 to 500, 50 to 200. So let me just write it. So this first one, let's say is from 20. It started at 20 and it ended at, let's say, 450. This one started at, let's say, 50 and it ended at, let's say, 250. Let's say this one started from 1,000 and it ended at, let's say, 5,000. Then this one started from 2 and it ended at 25. So you can see that each of the continuous attributes, they have different ranges. So this is the range of this one. This is the range of this one. This one is, it got to 5,000. This one just stopped at 25. You can see that the range of values, they are not uniform for each of the continuous values. So it turns out that if we were to feed all of these attributes into our AI model directly without doing some processing, the AI model that we develop or the deep learning model is not going to be very robust, and it's not going to be very good, and it will not do well. So we need to perform what is called processing, and the processing we are going to perform is called standardization. Standardization. So what is standardization? Standardization simply means that all of these attributes, you are trying to put them in a similar range. So if you look at this explanation, that it says that deep learning models are more easily trained if the attributes that are used to train them display values in symmetrical ranges, preferably low values from -3 to +3. So we want to put all of these values within a similar range. All of them, we want it to have a similar range. So typically from -3 to +3. So we want to transform all of these attributes such that they are within the same range. And as we can see from the explanation, if we do that, the model that we are going to be developing is going to be better and it's going to be much more robust compared to the case if we don't do standardization. So we are going to do standardization. So what does standardization, what does it mean? Standardization, there are different ways you can standardize, but the most robust way is called standardization, and is given by this formula. So when you have your attributes here, so let's say these are the values of your attributes, you find the mean. So let's say this x. So you find the mean. The mean is called x bar. So after getting the mean, you subtract each of these from the mean. Then after doing the subtraction from the mean, you will now divide by the standard deviation. So this is the mean, and this is the standard deviation. Standard deviation. So if you do this preprocessing step on all of these, you will discover that it's going to narrow the range of all the attributes into symmetrical ranges, and it's going to be easy for the deep learning model when it's actually developed. So this is before standardization. So look at this graph carefully. So I want you to look at this graph carefully. I want to show you the graph after standardization. Then somebody will tell me the difference and the similarity. So this is before standardization. So after standardization, this is it. So can somebody tell me the difference between the two? Will tell me the difference and the similarity. So what is the difference? So the range of values has changed. So this one is from -1 to 2. This one is from maybe -1 to 2 or so, -1 to 2, -2 to 2. So all of the attributes, they are now within a symmetrical range. They were not like before then, we're seeing some was going to 5,000, but now we can see that all of them are within the same range. So what is the similarity? Yes, the shape of the graph is still the same. So it's just the range of values you are changing. You are not actually changing the shape of the graph, and you are not actually changing the structure of the data set. So what this line of code is doing is standardization on both the train test and validation. So it's this algorithm. So if each of the data sets calculate the mean, then calculate the standard deviation, then subtract each of the data points from the mean, then divide each of the data points from the standard deviation. So it turns out that there is you can decide to use this algorithm, or you can decide to use the standard scalar class imported from scikit-learn, and it's going to do the standardization for you. So we are trying to pre-process the data. So after the pre-processing, we are going to build the dataset pipe. So what the dataset pipe is all about is simply is very straightforward. So for the dataset pipe, we want to determine what is going to be our input and what is going to be our output. So when you look at the yes. Okay. Yes. Thank you very much. So I actually missed that part. So we talked about preprocessing the continuous attribute. So after we process the discrete attribute. So if you look at discrete attribute, like I said, they are in two categories. So what we normally do is that, and if you look at, it's just similar to the continuous variable. Like this one started at 3, ended at 8. This one started from 70, ended at 82. This one started from 1, and it ended at 3. So we also want to put them in a symmetric range also. But we don't use standardization, we use another method. Can somebody tell me the other method that we think we can use for the discrete attributes? Okay, so one method we use is that, so this is 6 categories, 13 categories, and 3 categories. What we do is that instead of using all of these attributes directly, what we do is that we put these, we get all of the unique attributes. So then we put it in a form of an array or a list or a dictionary. So we put all of these attributes in an array or list or dictionary. Then when you put it in an array, the index to this value is 0, 1, 2, 3, 4, 5. The index to this is 0, then it will end at 12. The index to this is 0, the index to this is 1, and the index to this is 2. So when you put all of these unique values, when you put it into an array, then you get you put the unique values, you put them into an array, then you will sort them from the lowest to the highest. So when it has been sorted from the lowest to the highest, then you look at the index. So it is the index of the element you are going to use instead of the element itself. So that is the preprocessing we do on it. Because if we were to use the index always starts from 0, then it will end at its final value. So it always starts from 0 and to end at its final value. So it always starts from 0 and to end at its final value. So you are kind of also trying to put it in a similar range. So the starting point will always be 0, and the ending point is going to be the last value that is inside the array. So that's the form of preprocessing we do on discrete attributes. So let me go over it again. So for discrete attributes, you find the unique values, the unique categories, the different categories that are in that data set. So after finding the unique categories, you will now put it into an array. Then you will sort the unique categories from the lowest to the highest, from the lowest to the highest, from the lowest to the highest. So after sorting it is the index. It's the index, like this number 3 is indexed at 0. This number 4 is indexed at 1. This number 5 is indexed at 2. So it's the index you are going to use and you are going to feed into your deep learning model. It's not the actual attribute itself. So that's what you do for the discrete. So like you said, yes. We did also take account the frequency. This is the reprocessing we did. X minus x bar divided by the standard deviation. So x minus the mean divided by the standard deviation. We didn't take into account the frequency. The only reason why I talked about the frequency is just to show you a plot of the continuous attribute. So it's just for visualization purpose and to explain this question. So you are not receiving the frequency for both cases. Yes. Okay. For the discrete case, ordinal encoder. So this method that I've described to you is called ordinal encoder. For this continuous attributes, I said standardization, but there are other methods that you can use apart from standardization. But it's standardization I described to you. For this discrete case, there are other methods you can use. So what is the method I just described to you is ordinal encoder. So we continue. So after doing the processing, then you build the dataset pipe. So for the dataset pipe, all what we are simply doing is just to get our input. So our input, you get your output. So you just build a TensorFlow data set of the input and the output. Then you are going to put it in the tensor data set data pipe. So that's what we are doing. So we decided that of all the attributes, of all the inputs, the input we are going to be using is the horsepower. So it is the horsepower we are going to be using as the input, and for the output is the miles per gallon we are going to be using. So building the data pipe is just determining your inputs and your outputs. So for this purpose, we are building the tensor data set pipeline, the tensor data set pipe. Then you are collecting the input, which is the horsepower, then the output, which is the miles per gallon. So after building the data set pipe, the data set or data pipe, you are going to build data loaders. So data loaders is simply how you load in data, because after this data loader, that's when you can actually use your model. So after determining the input and your output, then putting it into a TensorFlow data pipe, then you build the data loaders. So data loaders is simply how you load data into the AI model. So in this case, you are going to be loading. It is not for any deep learning model you are working with. It's not, for instance, if to say the data set, if to say it has 400 rows, it's not all of the 400 rows and you are going to feed into your AI model at once. You are meant to feed it into the AI model batch by batch. So for the 400 rows, you can't feed in the whole 400 at once. That's not what we normally do. We feed it batch by batch. So that's called the batch size. So the batch size here is to specify the batches that you are going to be loading, the number of batches or the data set consisting of how many rows you are going to be loading into your model one after the other. So the data loaders we build, the batch size we define is 32. So we said that, so when we did that calculation, we got the training set, the number of rows for the training set, the validation set, and the test set. So when you are loading data, when you are trying to load it into the AI model, instead of, I don't know, how many did we get for this? 64. 67. 269. Okay, so this is what we got. So what this line of code is telling us is that when you are loading all of these values into the AI model, you put in 32. So you first of all load 32 of this. So after loading 32, then training your AI model on the first 32. If you go to the next 32, it's going to use that data set to further enhance the AI model. Then the next 32. So remember that the training set is 269. So it will go do this 32 until it exhausts the whole 269. So we are just saying that you should load how many rows you should load one after the other into the AI model. Then what this drop line simply means is that you know that this is in 32. So at some point there will be some left that will not be up to 32. So can somebody do the calculation? If you are loading 32 one at a time to this for this training data, the last set, how many will it be? Can somebody do the calculation for us? 30. So how do you do the calculation? 32 times 8 is what? 256. So 256 minus 269 is what? 13. So the last batch is going to be 13. So this last batch is not up to 32. So they say that the last one you should drop it because you can only load data sets in 2 raised to power x time. So 32 is like 2 raised to power 5. So the last one is not up to 32. So they say that you should drop the last batch that is not up to 32. So that's for building the data loaders. Then after that, we can now build the AI model. Now, yes? You can just set it. Yes, you can set it depending on your preference. But in this case, yes. Yeah. So you are saying the batch size does it have an effect? So the answer to your question is not that straightforward. But the answer I will give is that it's not supposed to have an effect on your AI model. It's not supposed to. So you are it's just the concept of batches is that you cannot load the full data at the same time. So you just need to put it into separate segments. And the separate batches should be 2 raised to power x. So depending on how you want to choose it. So you can do 2 raised to power 5, 2 raised to power 4, 2 raised to power 3. Yes.
Can you use like this different value like not an alpha to say you draw it and different command for it to not have 2 raised to power
Yes, it's possible. Such that maybe it does a 2 raised to power 3 on the last batch. Yes, so you can also revise the program to do that. So we are now going to talk about building the model. So this particular building the model, we have actually touched on it. So that was the part where we started with artificial neural network. But like I said, for the purpose of this class, we are just going to be considering the Python command. So I've told you I've done the lecture for ANN. We've finished that lecture. Then I also showed you a visual representation on playground TensorFlow, but now it's just putting it in terms of Python programming. That's what we are doing. So for an AI model, we have we've talked about artificial neural network. So we have the input layer, we have the hidden layers, and we have the output layer. So we are going to talk about the layers. So we are just going to specify the structure of the neural network here. So this is one way of doing it. So this line of code is just to specify the input layer. So this is the input layer, this is the output layer, and this is the bias. So I've not actually mentioned the bias, but I've mentioned it. It's just that I didn't say that the name is bias. So this is the simplest ANN model we have. So this is the input layer, this is the output layer. So I call this X1, then let's call this Y, then let's call this X0. So this is W0 and this is W1. So this is the simplest ANN we have. So Y is equal to W0 X0 plus W1 X1. But it turns out that X0 is equal to 1. So the X0 is always equal to 1. So if X0 is equal to 1, so Y is equal to W0 plus W1 X1. So I'm trying to show you this equation earlier. So it turns out that this W0 is called the bias. We call it the bias term. Then from here, if it's W1 X, W2 X2, W3 X3. So those are called the weights. So this W0 is called the bias term. So I've not actually said bias, but we've talked about it before. So this is trying to build the simplest AI model where you have your bias, you have your inputs, then you have your output. So if you look at the piece of code above, this is actually the piece of code. So you are importing touch.nn, which means a neural network. So you are trying to get a neural network. Then you are saying that this is a linear model, or this is a linear layer. Then you are putting the inputs, the output. So the number of inputs is 1. This is the input, X1. It only has one input. It doesn't have two inputs. This X0, so that I'm saying that it doesn't have two inputs, it has only one input. Because this X0 is equal to 1. So by definition is equal to 1. So we don't really count it as an input. So this neural network, it has one input and one output. Because this one is equal to 1. If to say this one was X1 and this one was X2, we say it has two inputs. But given that this is X0, we just say that it has one input, one output, and it has a bias term. So this bias term is given by this W0. So we've defined the neural network. Then so this line of code here is just showing, because within this neural network definition, there are some modules in the background that are working behind the background to do the initialization. Then the two most important modules are the init function and the second function called the forward function. So these are the two modules that are, or the two functions that are working behind the scene when you are actually defining the neural network. So I'm going to upload this notebook after the class, so you can run it for each of the cells. You can run it, but when you come to this particular cell, it's going to give an error. So if it gives an error, don't worry about the error, because you are just looking into the neural network class, because we said we define something like nn.linear. There is a class nn.linear. So within the high touch interface. So we are just looking at what is inside. So if you run that line of code I was trying to show you, it's going to give an error. And the reason why it's giving an error is because it's not actually part of the program. It's just trying to explain what is inside the neural network class. So we can see the structure of the ANN, so which I've drawn on the board. So you have the input layer and you have the output layer. So you can so when the model first of all starts, so this is the model. So this is the model that I'm saying. So this is the simplest model we are trying to use. W1 plus W1x. W0 plus W1 x1. So we said that x1 of x. Let's just put it as x. W1. Let's just say W and x. So since it's 1 and 1. So let's just remove the 1 and 1 that is there. So this is our so this is the simplest model we have. So this is the bias stem. So let me just show you this model up here. So in place of, so we have removed the W, the 1 and the 1. So it's now this. So y is equal to Wx plus b. So remember that W0 is the bias. So in place of W0, I'm just replacing it with b, which stands for the bias stem. So this is another way of defining the neural network. The first way we defined it was NN.linear. Another way, which is better, as you are going to be seeing, is when you have a model. This is the name, then NN.sequential. So the first way in which we defined it, we said NN.linear. That one is not really good in the sense that you cannot add in hidden layers. Remember we talked about hidden layers. So for that case, if you want to work with a linear model which has just one unique layer, one output layer, then you use that. But this one is better in the sense that you can put in the number of hidden layers we have. So we said that we call it a sequential model. So this is how to create a sequential model. Then you can add hidden layers to it. So for instance, if you want to add one layer, then call it linear, you can add it to the sequential model. Then it turns out that, so let me go to this part. So it turns out that we are listing the parameters of the model. So this line of code is to list the parameters of the model. Can somebody tell me the parameters of the model? Huh? Yes, exactly. Who said it? Okay. So the parameters of the model are the weights and the bias. So these are the parameters. So this is the a tensor flow containing the two parameters. So we don't know which is which, but we are still going to, there's a way you can write the code then to show you which one is the weight and which one is the bias stem. So we can see the weight and the bias here. So let's move on. So it turns out that we defined a sequential layer. There are other layers that you can define, but all of this we are going to return back to it later subsequently. It's because we are dealing with a linear model. That's why we are not including these layers, but we are going to return to it later. Then let's look at this let's look at this neural network. This neural network, it has one input layer, then an hidden layer, and an output layer. So how do you, if you want to, this kind of neural network here, if you want to specify it in terms of Python command, this is how you specify it. nn.sequential, then this and this. But somebody look at this line of code here. Maybe you know Python or not. Then look at this diagram up here. Then tell me, explain to me this code from this diagram. Just study it for a minute. Just study it for a minute. Then try to explain to me. It's not visible enough. Okay, this is the code. Let me write it here. nn.sequential, then brackets nn.linear 3, 5, nn.linear 5 and 1. That's the code. So looking at this picture and looking at the code, can somebody explain the code to me?
So the string index, the code is expressing that the three inputs are going to 5 layers, then the 5 layers are now converging.
Exactly. So it's very correct. So what this code is saying is that you have 3 inputs, 1, 2, 3. So the inputs, then the output is 5. We have 5 neurons in the hidden layer. So from this portion, then you have 5 hidden layers here, then neurons, sorry, not layers, sorry. So you have 3 neurons here. You have 5 neurons here. So you have 5 neurons here, and you have one neuron here. So this is representing the structure of the neural network. Do everybody understand this? Okay, so let me just say something. So for your exam, I'm not going to tell you to write Python code. Or I will give you Python code and I will tell you to explain it. So that's the structure I will do. Like for instance now, I can give you this code now and ask you that you should explain this code for me. So who cannot explain it in this class? Okay, you cannot explain it. Okay. So what this line of code is saying is that you are defining an artificial neural network. You are defining an artificial neural network. So NN stands for neural network. So it's a sequential model. So sequential simply means that the output of one will go into the input of another. So it's sequential. It follows like a orderly manner. So you have this, the input of this will go into this. So this becomes the output. Then this one will now serve as an input and to go into this. So this will now become the output. Then this is, you are defining a linear network. So like I said previously, that these equations, they are linear equations. Then we are defining a neural network, and it's a linear neural network. The first layer, it has 3 neurons, so this is the queuing. The second layer, which serves as the output, it has 5 neurons, and this is the 5. So this represents this now. So given that it's sequential, this is like the input and this is the output. So this has another layer. So this is the input, this is the output. So for the next set of layers, this will become the input and this will become the output. So this one has 5 neurons in the input and it has 1 neuron in the output. So that's the explanation. So like I said in the exam, I can just give you this code and I will tell you to draw the neural network representation for me. So you should know what to do. So, like I said, I'm going to give you this notebook, but if you run it, it's going to give an error. And the reason why it's going to give an error is because the neural network we are dealing with, it only has one input and it only has one output, because we've already specified our input and we've already specified our output. So it doesn't have 3 neurons in the input. So it's going to give an error because it's just an example I'm trying to show. So if you run it, it's going to give an error. So we now talk about making predictions. So it turns out that, so I talked about the weights and the parameters. So it turns out that the weights and the bias, they are called the parameters of the ANN model. And I've been talking about these values, and I've been talking about these values, and we've written equations. I've talked about the weight and the bias several times, and we've written the equations, giving polynomial models. So I want to ask a question. Can somebody tell me how these weight and bias, they are called the parameters of the ANN? Like in our last lecture, when I showed you that visualization in the TensorFlow playground, I told you that the weights they were updating after each effort, after each iteration. But can somebody tell me how these weights are generated or how they might be updated? Huh? Yes. Okay, so both of them are right. So I want to ask, initially, so they taught me how those weights are updated. But initially, these weights, they are first of all, at the first time of initialization, how are the weights, how are they gotten? Yes, exactly. So they are gotten randomly. So it turns out that these parameters, they are gotten randomly. And after each iteration, they are going to be updated, like they said, using the gradient descent and loss function. So let me just I will just write some equations on the board. And I will try to explain it in the context of what is happening in the Python code. So the loss function, I want to define the loss function. The loss function, let me define it as, let me call it J of omega, and I will define it as 2n I starting from 1 to n, then h of omega x minus y squared. So this is the loss function I defined. Then the weights, so this is the loss function now. So it's called the cost function, but in this context, let me call it the loss function. Then the weights, how are they updated? They are updated, wi is equal to wi minus alpha, the partial derivative of the cost function with respect to the weights, wi. So that's how the weights are updated. So this equation updating is for updating the weights, or updating the parameters. that x is equal to w naught plus w1x1. So this is the linear regression model we are working with. So we have explained. Then W no, this is the general equation of how to update the weight. So how is W naught? How is it updated? It's updated according to this equation. Then how is W1 updated? W1 is updated according to this equation. So this is how you update W1 and this is how you update W1. Yeah, W1 is W1. Yeah, this is alpha. Alpha is called the learning rate. Then this is the partial derivative of the loss function with respect to the weight. So let me try to explain this equation. So what did I call this? This equation, what did I call it the last time? Okay, so I called it the mean square error. So why is it called the mean square error? This h of omega is the linear regression model. So it's the ALM model. And this is also called the prediction. So this is the model that we are trying to develop. And it's called the prediction. But this y is the actual output, is the actual target. So when you look at the prediction and look at the actual output, so you are trying to minimize the error between the prediction and the output. So after subtracting the prediction from the output, you square it. N is the mean. N is called the mean. So you square the error, then you divide by the mean. Then this one is just a factor. So that's called the mean square error. So for the AI model, we want the error to be as low as possible. So when we are on TensorFlow playground, remember it was showing the loss on this side, on the right hand side, and the loss was reducing. So we want that loss to be as minimum as possible. Then this is how you update the weight. So like I said, this weight, and like you widely responded when I asked the question, first of all, they are randomly generated. They are randomly generated, but they are updated according to this equation. So this is the equation for updating the weight. So this is what you have here is the partial derivative of the loss function, and it's also called the gradient. So that's the j omega t omega I is called the gradient. So that's where the gradient descent algorithm, that's when it came from. So when she talked about the gradient descent algorithm, so this is the gradient descent algorithm. The gradient descent algorithm is used to update the weight. Then in the gradient descent algorithm, this expression, the partial derivative of the loss function with respect to the weight. So it's also called, this gradient is also called the change in loss, because this is the loss function. So the loss function is changing divided by the change in weight. So this function is also called the change in loss divided by the change in weight. So this is the general function for the gradient descent algorithm. So this is the function in which you use to update W naught, because W naught is also called what? The bias. So you update W naught according to this equation and you update W1 according to this equation. So this, how did we get this? How did we get this? So the derivative of the cost function with respect to omega. So look at it. So this is the cost function. So when you differentiate this with respect to W naught, because essentially this is the general equation, but for W naught, it becomes W naught minus alpha the j omega the W naught, then W1 becomes W1 minus alpha the j omega W1. So who are the people that understand how I got from here to these two? So what did I do? What did I do? How I got from here to here? What did I do? Okay, yes, so that's what I simply did. So in this case, we are differentiating this with respect to W naught. And look at it, this is the equation here. So when you are differentiating this with respect to W naught, so let me write down the cost function very well. The cost function is equal to 1 over 2n. I is equal to 1 to n. H of omega x. So I'm just simply writing this cost function. But in place of this h of omega x, I'll put this one. I'm putting this one. So W naught plus W 1x1 then minus y. So this is still our loss function. This is our loss function. So for this, we are differentiating with respect to W naught. So when you are differentiating with respect to W naught, it's just simply because W naught, it has no xm. So it's just simply h of omega x minus y. So, and these two will come down. Remember, you are differentiating. These two will come down. So the 2 will cancel 2. So it's now 1 over n. So that's why you have this. So when you are differentiating with respect to W1, so W1 has an x at the back. So it's simply this equation then multiplied by x. So remember when you are differentiating and there is like an x term here. So the x term will come over, we multiply the whole equation. So that's how we got these two equations. So these two equations just simply means how you update the weight. So like I said, this is called the gradient, and this is called the gradient descent algorithm. So how does the gradient descent algorithm? Yes? Okay, how I got this? Okay. So using this formula, differentiating this one with respect to W naught. So I'm differentiating this equation here. So this is the equation here. So with respect to W naught. So we are differentiating this equation with respect to W naught. So when you do the differentiation, you can remember your differentiation that these two will come down. So if these two come down, the 2 will cancel 2. So it becomes 1 over n. So that's why you have your 1 over n here. Then you are differentiating with respect to W naught. So since there is no any coefficients after W naught, so the differentiation will just equal to this. So alpha, then your differentiation is 1 over n. The 2 will come down. So the 2 will come down here, then it becomes this. But when you are differentiating with respect to W1, so we've differentiated with respect to W0 and we got this. Now we now want to differentiate this equation with respect to W1. That's what we want to do. So remember your differentiation. These two will come down. So 1 over n. But there's an x1 here. So after this one coming down, this x here would multiply the whole of this equation. So that's why you have this x here. Because here we are differentiating with respect to W1, and here we are differentiating with respect to W0. So it's just given by the expression. So we are differentiating with respect to W0 and we are differentiating with respect to W1. So that's why we have this. Do you understand better? Yes. What is it? Which x are you talking about? This W1. There's an x, yes. So the prediction model, is it this? This is the prediction model. No, we are not putting it back into the prediction model. What we are simply doing is that we are trying to get the equation we are using. We want to derive the equation for updating weights. So this is the gradient descent algorithm. Then all what this x is saying is that because for this x, it came from here, you are going to differentiate this cost function with respect to W1. So this is the cost function here. Then we'll differentiate it with respect to W1. For this one, we are differentiating it with respect to W0. This is W0. But now we are differentiating it with respect to W1. And this is W1 over here. And given that this has a coefficient, that's why in differentiation, the power will come down, then the coefficient will come out of the equation. So the power came down, the coefficient came out. For this W0, there's no coefficient multiplying W0. So there's nothing for it when you are doing the derivative to multiply it by. So this is the gradient descent algorithm. And so it is the algorithm the computer uses to update the weight. So let me give an example. Let's look at this data set. Let's look at this data set. Then let's try to do the operation by hand. We will do the calculation based on all of this. Then after doing the calculation by hand, we will try to use Python to help us to do it. So look at this data set very well. This, which I presented before. So this is our x and this is our y. So 130, 165, 150 and 140. 150 and 140. Then the y 18, 50, 16. 18, 50, 60, and 17. So if you are given this data set now, and you want to compute the weights, and you want to get an approximation of the linear regression model, so this is what you do. You calculate W0 plus W1x1. After doing this calculation, then this one is equal to h of omega. Then after that, you do h of omega x minus y. You do the calculation. Then after that, you do h of omega x. H of omega x minus y. Then all of it multiplied by x. You do the calculation. Then you do one last calculation. H of omega x minus y all squared. Then you do this calculation here. So we want to kind of simulate how the neural network, like all of this, is just a line of code you will type, and it's going to give you the weight. But I want to go through the algorithm for you to make you better understand what is happening behind the Python code. So this W1 and W0, they are the weights, and like you said, they are randomly generated at the first instance. So the first instance is randomly generated. Then after the random generation, that's when it begins to update. Let me just show you the gradient descent algorithm. Okay, so this is the gradient descent algorithm. So start with a random choice of weights. So that's where you first of all start with. So let's say W0 is equal to W1 is equal to 0. So we are starting randomly now. So given this, what's going to be here? Okay, 0, 0, 0, 0. Who doesn't understand? So x, so this is our x. So let's just put wx. So this is our x. So what's going to be on this row? Minus 18, minus 15, minus 16, minus 17. So what's going to be here? So this we just multiply by x. So you should just multiply it down. So let's put my right hand. Yeah. Then this is the summation of all of this. This is the summation of all of this. So why do we need to sum it? Because or to update the weight, you have to sum. After doing this, you have to sum it. So that's where this summation came into play. And why did we sum this place? So because in the equation, after doing this, and after multiplying it with x, there is this summation there. So you have to sum it. So once you've gotten all of this value, then you update the weight according to this equation. Let's say alpha is equal to 0.01. Alpha is called the length weight. So W naught is updated by the initial weight is 0. The initial weight is 0. So it's 0 minus 0.01, which is the learning weight, divided by n. What's n here? N is not the mean. Sorry, n is the, sorry. So it's not the mean. It's the number of samples. Sorry. In this case, n is not the mean. Sorry. N is the number of samples. This equation here, this equation is sum squared error. It's sum squared error because I'm not dividing by the mean. I'm just summing the errors and squaring it. So sorry, it's when I divide by the mean. That's when it's called the mean square error. So n is the number of samples. So what's the number of samples? Then times this summation is minus 66. Then to obtain W1, the initial weight is 0. Then 0.01 divided by 4 times minus 9595. So what will you get? Then one last thing you will do is to get 0.165. So here, what will you get? What will you get here? 33.998. So this is what you get. So at the first iteration, it's randomly, the weights are random. So that's select to 0. So when you go back, these are the new weights. So this is for the first iteration, for the first echo. So for the second echo, you are going to put in the new weights that we got. You are going to put it into this. So after putting the new weights into this, you will get new results, you will get new updated weights, and that will be the second iteration. So for the third iteration, you will put in the new weights, then you keep on, but that's how the algorithm, that's what the algorithm uses to update the weight. So, can somebody, so the loss function here is called, this is the loss function here. So the way we do it, so all of this that we've just done, I just now want to explain it using Python. So I'm not doing anything spectacular. So we've already done it in calculation. Then we just want to just explain it using Python. So what we did, what this code is just doing is that a random weight initially was first of all defined. Then using the random weight, we used it to make predictions. So this is the prediction. So what is showing here is some predictions of the based on the inputs. So you are trying to make the predictions. That's what we are doing here. Then here, we are defining the loss function. Then the loss function that we are defining is the mean squared error. So first of all, we got the error, the prediction minus the output. So what this line of code here is doing is just what we did here. The prediction minus the target. So when we do this, we got the following output based on our data set. Then after that, we squared the mean. Sorry, we squared the error and we divided by the mean. So what's happening here is we squared. This is the error. This is the error because it's the prediction minus the output. Then we squared it. So this is where we squared it. Then after squaring it, you will sum it. So you can somebody do this summation for me. 1094. So we squared it. So after squaring it, we now summed it. Then we divided by the mean. So what's the mean of this? What's the mean of what's the mean of X? 146.5. Okay, so when you do this, so that is the loss function. So in this case, the loss function is it's just this divided by the mean. So in place of 1/2n, which is the normal samples, it's just 1 divided by the mean. So that's the mean squared error. So if you put this equation, it becomes the mean squared error. So that's what we did here. So we got the loss based on this. So we want the loss to be as low as possible. So instead of going through all this equation, you can just call this PyTorch function and it will just give you the loss, the mean squared error loss. Then it turns out that we've talked about the mean squared error. The mean squared error is called the L2 loss. There are other types of loss function. Mean absolute error. So can somebody try to write the equation for mean absolute error for me? What would be the equation for mean absolute error? Can somebody try to come and write it on the board? You can just Google it. Just Google it. Then come and write it. The equation for mean absolute error. Then another person should Google the equation for. So for regression tags, these are the loss function you will use. Then for classification tags, these are the loss function. So can somebody just try to Google the equations and try to come and write it on the board for us? Otherwise, I will give you as an assignment. Somebody should Google it and write it. What I'm using is the sum squared error. Well, it's actually the mean squared error. So this one is the mean squared error. This is the mean squared error. When you divide by the mean, but I didn't divide by the mean, I divided by the number of samples. So that's why I call it sum squared error. So it's actually the mean squared error. called the mean square error. That's why you divide by the mean. It's called the mean square error. But in this case, it was the number of samples that was using, which is 4. So in order to let me correct myself. To correct myself, instead of using 4, we use the mean. To actually get the right answer. So use the mean instead of using Yes. That's the mean squared error. After squaring the mean, after squaring the error, you divide by the mean. Yes. Actually, the square. Yes. Yes. So there was 2n. I wrote 2n before. And that n is the number of samples. But the mean is the mean squared error. You need to use the mean. So can somebody? Yeah.
We are still using that some square differentiation. It was not changing to me. That typical she cannot have said it. So it will affect the formula we have for the before.
Yes, you're right. Why you differentiate? Because now this is the mean. So the 2 here is going to come here. So this is going to be 2 divided by the mean. So apart from that, what does it change? No, apart from that, there will be 2 here. There will be 2 here. Yes.
So what are the number of samples? So what's my
And you are not going to use it any number of samples because you are replacing it with the mean. You are replacing it and equals to b. So just try to do everything again. Let's spell it with this. You mean all the number of samples. Just try to do everything. So category. Well, okay. You have to know this how to do it. So can somebody tell me can somebody Google the equation for this and come and write it? Who has gotten it? The loss function, negative log likelihood, just Google it and come and write the equation on the board for me. So who is doing that? Who is doing that? Who is doing that? Nobody is doing that. the loss function for the first two. So just try to find out the equation for, so this is for regression tax and this is for classification tax. So in this piece of equation, we are just trying to update the weight. So the weight is updated by this factor, but it's not using the gradient descent algorithm. Then we got the predictions. Then here, we are just trying to, so after getting the predictions, what we are trying to do is that we are trying to find gradients. So remember I told you that the gradient, this is the gradient, the change in the loss divided by the change in the weight. So this is what we are just trying to do here. Then the backward function is the one that actually returns the gradient for the weight and the gradient for the bias. So this function, what this one is doing is to return the gradient for the weight and return the gradient for the bias. So essentially, it's just trying to do this, which is the gradient for the bias, and this is the gradient for the weight. So in place of the calculation we're doing, you can just put in this Python command. Then here is the updated weight. So what this line of code, so please give me 10 minutes because I just want to round this up. So sorry about that. So what this line of code is doing is essentially updating the weight. So we are trying to update the weight. So this is the original weight. Then it's trying to update it by this learning rate. And this line of code is trying to update the bias. So essentially, what the remaining of this notebook is all about is we've already done it. It's just trying to represent it in form of the Python command. Then we talk about the learning rate. Can somebody tell me the importance of the learning rate? So the learning rate actually, so I define this as the learning rate. So the learning rate is a very important hyperparameter in deep learning. So it's not called a parameter, it's called an hyperparameter. The weights, these weights of bias, weight and bias, they are called the parameters of the model. But the learning rate is an hyperparameter. It's not a parameter, it's called the hyperparameter because you don't, it's not, it's the learning rate is called a hyperparameter because it's not a parameter like the weight and bias, but a parameter of the learning process. So it's the most important hyperparameter of all. And it's used to, that learning rate is really a very important feature. And we illustrate it with this graph. So if the learning rate has to be just right. So if the learning rate is very high, you know, this is a plot of the loss as a function of the epoch. Epoch is the number of iteration. If the learning rate is too high, the loss is not going to be reduced even as the number of iterations increase. It's just going to be stuck in one place. That's if it's too high. Then if it's too low, the model here is when it is too small. It's going to converge, but it's going to converge very slowly before it reaches the minimal loss. But if it is just right, this red is when the learning rate is just right. Then with 5 iterations, you would have gotten the most suited learning rate you want. So the learning rate just determines the convergence of what? Okay, yeah, the rate of convergence to the good solution. Then we talk about optimizer. So I've already talked about optimizer, but I've not actually said that this is an optimizer. So can somebody tell me where is the optimizer? This is the loss function. Because look at this graph. It's after you define the loss function, you have to define the optimizer. Can somebody tell me this loss function? Can somebody tell me the optimizer? Where is the optimizer? It's there. By this is the optimizer. Where is the optimizer? Somebody tell me. Like I've already said it many times. Why I did say that I didn't call the name optimizer. Exactly. The gradient descent algorithm is the optimizer we are using. So it's called an optimizer. So what's an optimizer? An optimizer is just used to update weights. So there are different kinds of optimizer, but the one I talked about in this course, in this class, is the gradient descent. So it's called stochastic gradient descent optimizer. There are other kinds of optimizers. Can somebody tell me the other kinds of optimizers we have? Adam. Who has heard of Adam optimizer? Yeah, so Adam is another form of optimizer. So let me just list. So in case you want to use the Adam optimizer, so like I said, all these things we just did, using a line of code, you can do it. So this is the line of code that if you want to use the Adam optimizer. Can somebody tell me for the gradient descent, what will change if you don't want to use the Adam optimizer? What are you going to change this line of code to? SGD, which stands for stochastic gradient descent. So instead of this Adam, you just change it to SDG to use it. So, like I said, they are already Python. Like I will not in the exam, I will not give you this thing to do in the exam. So because I don't know, I feel it's a waste of time. I'm from experience. I think all the exam, you guys are really there. Nobody gets the answer correctly. So there's no point giving you this in the exam. So you can just use, like I said, it's just a line of code. And like I said, I will not tell you to write a line of code. What I will do is that I will give you a line of code and I will tell you to explain it for me. So that's what I would do for the exam. Yes? Yes? So the remaining of the class, like I said, is just putting everything into equation. So these are the different kinds of optimizers we have. So these are the different kinds of optimizers we have. Then I've already presented the gradient descent algorithm to you. Then just putting everything together. So this is just trying to put everything together. Then this particular place is when we try to loop. So remember that is dealing with batch. So when I first of all present that batch, it was just for one batch size. So to cover all the batches, you have to put a for loop, then just do everything here. So define the loss function, then present the optimizer, then you try to, okay, let me stop here. So we are going to, so here is just the training loss. So for each iteration, remember we are trying to minimize mean square error. So the loss is expected to drop for each iteration. Then here we are trying to compare the prediction with the actual target. So when we did the comparison, the prediction is not really great. And this shows that a linear model is not sufficient for a neural network task. So you have to introduce non-linearity. Then of course, after that, you make predictions. So here is just the previous code we worked on, but considering the number of epochs, so that's the number of iterations. So you keep iterating. So when you do that, you get this. So this is the training loss, and this is the validation loss that is plotted. Then this is just a visual representation of the training set and the validation set. So you can see the kind of model. But this particular class or the particular model we developed is not a good model because it's a linear model. So how can we make it better? We make it better by introducing non-linearity. In the previous class, what did I tell you? Yes, so that's the part we didn't do. So for the next class, we try to introduce activation function. So can somebody tell me where we would introduce the activation function? Where are you going to introduce the activation function? Which equation? Yes. So that's where you introduce the activation function. Then if you want to introduce the activation function, this is the code you are going to use. So in the previous class, we didn't introduce any activation function. So for this code, what is the activation function are we using? ReLU. Yes. So ReLU stands for rectified linear units. So that's the activation function we are introducing. Then there are other kinds of activation function: sigmoid, tar, ReLU. So under ReLU, we have different types of ReLU. So just try to read this. So by next class, which is tomorrow, we will have a class 5 to 6. So I want you all to come with your devices because we'll be using Google Colab to write some code and to understand it. So please, every one of you, please try to come with your laptop so that, because we'll be programming for tomorrow's class. So thank you very much.